Hello there, this is chapter 8.2, and in this lecture we're going to continue to discuss some more of the electrophilic addition reactions. Let's have a look at the video breakdown. There will be two videos for this lecture. The first looks at the halogenation reactions of alkenes, and this involves the addition of a diatomic halogen across a pi bond, and in the second video we'll be discussing the formation of a halohydrin, and this involves the addition of a halogen and an alcohol group across a pi bond. The addition of bromine across a double bond requires the use of a non-nucleophilic solvent. Any idea why? Pause the video and resume when you think you have an answer. Seeing as these are ionic reactions and the carbocation or electrophilic carbon always reacts with a nucleophile in the second part of the mechanism, then using a nucleophilic solvent would give an undesired product. Carbon tetrachloride is a tetrahedral molecule and is non-polar. And this is despite having the carbon-chlorine bond dipoles. So it does not behave as a nucleophile, but it will still solubilize organic reagents. The addition of a diatomic halogen across the double bond yields vicinal dihalides. Let's look at the mechanism of halogenation now. In the first step of the mechanism, known specifically as bromination because of the use of bromine as an electrophile, bromine approaches the double bond, and as this happens, an induced dipole in the bromine molecule forms, whereby the electron density is moved towards the green bromine atom and the red atom has an induced partial positive charge. As part of a concerted reaction, the diatomic bromine heterolytically cleaves, and it is during this process that a cyclic intermediate known as a bromonium ion forms. For any halogen involved in this process, this is known more generally as the halonium ion. In the second step of the reaction, the green bromine nucleophile attacks from the backside, think SN2, and this results in an anti-addition overall. Hopefully you can now see why it's important that there's no other nucleophile hanging around and why we use carbon tetrachloride as the solvent. However, the bromide is able to attack from either end of the bromonium ion. So the original cis-trans stereochemistry of the alkene is important when thinking about the types of addition products that will be possible. Here we only have two products because the original alkene was symmetrical and bromine was added to a cis alkene. Here is butene, and we can see that it has two possible stereoisomers. That's the cis stereoisomer that we just looked at the mechanism for, and also there is the trans stereoisomer which we're going to look at the mechanism for. Both of the addition products will have an anti-conformation. However, for the cis or Z alkenes with symmetrical R groups, a racemic mixture of enantiomers are formed. But for the trans or E alkene, which bears two identical R groups, this will lead to the formation of a meso compound. So let's look at the addition products for the cis alkene more closely and then look at the mechanism for the trans alkene afterwards. Here are the cis addition products again, and we can see that there is a mirror plane for these products and that they are indeed enantiomers. So there is no internal mirror plane when you rotate the molecule, put it in an eclipsed conformation and to check this out. And the stereochemical designation for the left-hand enantiomer is SS, whereas the stereochemical designation for the right-hand enantiomer is RR. So this means that we have a racemic pair. Let's now look at the mechanism for the trans alkene. The mechanism for the trans alkene, of course, is exactly the same first step as before. Also remember that the attack can come from above as well as below the pi bond. Here it just so happens that the attack of the electrophile is from above the pi bond. If you imagine a side-on perspective, the methyl group on the left is closest to us, and this is why it ends up being on a solid wedge. However, the methyl group on the right would be furthest from us, and this is why it ends up on a dashed wedge. The hydrogen atoms accordingly are on a dashed and solid wedge from left to right respectively for the same reason. Let's have a look at the second step now. As before, the bromide nucleophile will attack in an SN2 fashion, and that is from the backside. So we call this an anti-attack, as it will lead to the anti-addition products overall. And then just like before, that attack can be from either end of the bromonium intermediate. At the moment, you may be thinking, well, why are these in fact meso compounds? So let's take a look on the next slide. When the bonds are rotated for each of these addition products, we place them into an ellipse conformation, and then you'll notice that there is an internal mirror plane. And this is the characteristic hallmark of a meso compound. So in other words, these two addition products are one and the same.
This concludes part A.
In this video, we're going to take a look at what happens when halogenation is carried out in the presence of a nucleophilic solvent. In this case, the solvent is water. And when an alkene is reacted with a halogen, that's either chlorine or bromine, in the presence of water, then a halohydrin is formed. This places a halogen atom and an alcohol group in a vicinal relationship across the double bond. This is known as the halohydrin. A Vic dihalide is also possible as a minor product in the reaction. Let's now take a look at the mechanism. In step 1, just like in the halogenation reaction, the halonium ion is formed. However, in step 2, because water is the solvent and there is a greater concentration of this nucleophile, it attacks the halonium ion in an SN2 fashion. This results in a protonated halohydrin with anti-stereochemistry. The final step of the reaction is whereby a proton transfer occurs between the solvent, water, and the protonated halohydrin to yield the halohydrin itself and a hydronium ion. Now, what would happen if, for example, one end of your alkene substrate is more substituted than the other? So here we would be thinking about the regiochemical outcome of such a reaction. In the case of halogenation, the formation of a vicinal dihalide does not have any regiochemical outcome, whereas the formation of a halohydrin is regioselective. Here we have a bromonium ion that is bridged asymmetrically because the tertiary carbon is able to accommodate more of the positive charge than the primary carbon. And this means that the water will attack the more stabilized positive charge, which is shown in the second step. Lastly, the protonated bromohydrin undergoes a proton transfer to yield the halohydrin as before.
This concludes part B.